Hi everyone! So now it's time to practice what we learned in the previous lectures about type parameters. And in particular, I would like to use these exercises to showcase how generic types and functions can improve the way we design and test our program. So let's open the file generic function exercises. First, we're going to implement a couple of methods for pair. Pair is a generic data type, and we can tell because of these square brackets just after the class name. So pair has two fields called first and second, both of them of type A. In a sense, a pair is like a tuple, except that both first and second must have the same type. And here we have a couple of examples. Names, which is a pair of string, John and Elizabeth, and ages, which is a pair of int, 32 and 46. Cool, so now the first method to implement for pair is called swap. Swap creates a new pair where we exchange the position of first and second. So if we call swap on the pair John Doe, we get back the pair Doe John. Make sense? So now please pause the video and try to implement swap. So to create a pair, we can use the new keyword. This is something we can do for all classes and trait. Then we can pass the current value of second in the first position, like this, and the current value of first in the second position. Note that we could have used this.second and this.first to clearly express that first and second comes from the current object, this. However, this syntax is not idiomatic in Scala, and generally we tend to skip it whenever we can. So we remove this. Another thing we can do here is to remove the new keyword, like that. You might remember from the val versus def lecture, where we saw that whenever we have something with .apply, we can remove the .apply part. So this is what happens here. Behind the scene, we are calling pair.apply, and we can do this because pair is a case class. The case keyword is important here. It makes the compiler automatically implement a few convenience methods for us. Things like toString, equality, or hash code. But it also adds an apply method in the companion object of pair, even though we haven't created such an object yet. By the way, the companion object of a class is a concept very specific to Scala. It's basically an object that has exactly the same name as another class or trait. For example, here, if I create a class, let's call it user authorization, then I can create an object, user authorization, and that would be its companion object. What are they used for? For a few things that we'll cover throughout the course. But for now, we can think of them as a place where we can put functions and values related to a class that do not require an instance of the class. For instance, static methods or constants. We'll come back to that concept later on. Cool, so another question is, how do we test swap? Let's open the corresponding test file, and let's write a simple example. So let's say pair 01, and then we call swap on it. We'll expect to get a pair 10. So we'll transform it to an assertion. And maybe we could test with a pair of string, like John Doe, for example. John Doe, and we'll expect to get back a pair with Doe, John. Let's run the test. It works. What next? What are the other test examples or properties that you would want to add? Please pause the video and take a minute to think about it. It turned out that we don't need any other tests. In fact, we can even remove the second example. Because swap is generic, so we know that it can't act based on the values of first and second. In other words, we have the guarantee that swap must treat first and second as black boxes. So if swap exchanges the elements for a pair of int, we know it will behave in the same way for all other pair of int, and indeed for pairs of any type. The only thing we need to be careful of is using different numbers in our test example. For example, if we had tested with a pair 1, 1, we would not have covered all the possible cases. Swap could very well duplicate the first value instead of swapping it. Now let's go back to the exercises and implement map for pair. So map probably does what you would expect. It takes an update function from A to 2. A is the element type of the input pair, and 2 is the element type of the output pair. And we're going to apply this update function on both first and second, such that if we call map on the pair John Doe using the length as the update function, we would get back the pair for 3 because John contains 4 letters and Doe 3. Okay, now it's your turn to implement and test map, so please pause the video and have a go. So we need to create a new pair, and then we apply the update function on first and then on second. That's it. Now, how do we test map? Like we saw in the lecture, we are guaranteed that the update function will be used to produce all the elements of the output pair. This is because map returns a pair of 2, and the only way to produce a value of type 2 is to call the update function on first and second. So this means we don't need to test with several update functions. We can use the simplest possible one, the identity. So let's write a test example. So we'll say pair with a simple pair like pair 0, 1, and we're going to map it with the identity. And basically we expect to get the same pair back, 0, 1. It works. Do we need any other test? No, we don't. In the lecture, we had to test with lists of different sizes, because map could theoretically behave differently for small and large lists. But for pair, this is not possible, because the size is fixed. It always contains 2 elements. So we only need one test to check that map is implemented correctly. So let's go back to the exercises, and this time let's jump to question 1D. Someone encoded a secret message inside of this pair, and our goal is to figure out what it is. Note that every number in this list represents a character which may or may not be in the right position. So one thing we might want to do is to create a Scala worksheet. It's kind of a playground to try some code and visualize the results. So for example, with IntelliJ, we can go to the project directory, then create a new file, and we select Scala worksheet here, say secret. Then we would need to import our exercise file, so function exercises. And now we can put secret here and run it, and visualize what is the, how does it look like. So we can see like the list of bytes. And for example, if I say secret map and I reverse all the array inside it, I should be able to see the difference, as you can see here. Now, if your IDE doesn't support worksheets, another thing you could do that is not as good is to use a failing test. So you could say val tmp equals secret, or secret map reverse, as I just did. And then you could assert that tmp is equal to a pair of empty string. And we would expect this test to fail, but the good thing is when it fails, we can actually see, oh, did I run something else? Yeah, so this did fail, and you can see this time that we didn't get what we expected. So this way, it would be a good way to visualize what happens. So please pause the video and try to decipher this message. Okay, so we know that secret contains a list of bytes, and we want to get some kind of string out of it. So let's try to convert this list of bytes into a string. So we use map for this, and let's use a string constructor, and here we can display all the possible options. So we could potentially pass a string, an array of character, an array of bytes. So probably an array of bytes. But what we have is a list. But it's quite easy to convert a list into an array. We can just say toArray. Let's run it to visualize what's happened. OK, so now we get letters, but they don't make much sense. One thing we can notice here is that they both end with a capital letter. So maybe that these two strings are, the other way around. So let's map again, but this time we'll reverse the string. Note that I could have called reverse here, but I quite like this pipeline like kind of API. So it's a bit more inefficient because we're going to create some intermediate pairs, but to be honest, we don't really care about performance. So let's run it. I actually have this bug from time to time. I have to kill it and restart it. OK, so now we have programming functional. So these words make sense, but not necessarily in this order. So we want to put functional first and programming next. So let's call swap for this. Let's run it. Let's kill it and run it. Cool. This time functional programming. So this is probably what we expected. Cool. So this was just an occasion to play with our pair API, but also to discover worksheets, which are a useful tool for exploring APIs, even though, as you can see, it has some bugs. Now let's go back to the definition of pair, where we have one method left to implement, zipWith. zipWith is a method that lets us merge two pairs together using a combine function. So let's have a look at a few examples. If we have the pair 02 and we zip it with the pair 34 using plus as a combine function, we get back the pair 36, 3 because we sum up 0 and 3, and 6 because we sum up 2 and 4. Another example, if we zip the pair 23 with the pair hello world using the combined function replicate that we saw in the first lecture, then we get back the pair hello hello world world world, where hello is repeated twice and world 3 times. So now please pause the video and try to implement zipWith. So this method may seem intimidating at first because we have two type parameters and it takes a function as an input. However, if we take a minute to look at the signature of zipWith, it turned out that we don't really have much choice as to how to implement it. We need to return a pair of type 2, and we don't know what is 2. The callers of the method will decide later. So the only way to produce a value of type 2 is to use a combine function. OK, so this is enough to write a good chunk of the implementation. So we can create a new pair, and we know that each field will be produced by combine. So combine takes two arguments, and because we don't know what we need yet, we can use triple question mark. It's a nice trick that we can use whenever we want our program to compile, but we still have some missing pieces. So let's check. Yes, it does compile. OK, another thing we could do is to annotate each triple question mark with the expected type. It's not mandatory, but it's kind of helpful. So we know that the first one is an A, the second one is an other because of combine, then the third one is an A, and the fourth one, other. Cool. So what we have done so far is the only possible code for zipWith. There is no other way to create a pair of type 2. Now the only thing we still need to do is to replace each triple question mark with the appropriate value. So in a sense, it's like a puzzle with only 4 pieces, which is a far less intimidating task than the one we started with, isn't it? So for the first triple question mark, we know that it's of type A. So it must come from the current object. It can either be first or second. Now if we look at the examples, it seems that zipWith starts by combining the first element of the two pairs together. So here we can write first, then here we'll write other.first, and it's the same pattern for the second one. So we'll say second, and here other.second. That's it. So now the question is, how do we test it? So please pause the video and try it out. Well, we can use any of the two examples up there. So let's take this one. Let's open the test file and let's convert it to an assertion. We'll run the test. Yes, it works. Do we need anything else? No, because as we saw when we implemented ZipWiz, the only point at which we had a decision to make was when we replaced the triple question mark. So we could have, for example, combined the first element of the current pair with the second element of the other pair. So as long as our single test verifies that we have combined the right elements together, then that's enough. This really shows the power of generic functions. Yes, it's convenient that we can zip any pairs together without any code duplication. But the most important thing is that this function is really straightforward to implement and to test once we learn how to use type parameters. Now let's practice a bit with ZipWiz. So let's go back to our test file, and here I created a class called product, which has two fields, name and price. And the goal of this exercise is to take a pair of strings that represent product names and a pair of doubles that represent product prices, and to combine them together into a pair of product. So for example, we expect by zipping these two pairs, we expect to get this one. So please pause the video and have a go. So we know that we want to zip these two pairs together. So let's say product.names ZipWiz product prices. Okay? And now we have to write the combine function. So it takes a name and a price, then we have an arrow, and now we need to return a product. So we can say product name price, and that's it. Now it's a bit annoying again to repeat because to define some inputs and to use them straight away. So as we've seen in the previous exercise, we could actually get rid of this and replace each argument with an underscore. Now you see here, IntelliJ is kind of giving me a hint that there could be some more refactoring we could do. So in IntelliJ we can use Alt-Enter and follow the guideline, and so now it proposed to replace to product. Why does it work? Because it's equivalent to do product.apply, and we know that product.apply is a function from string to double, so that's exactly the combined function that we want. Perfect. So I think this example is quite concise and it's quite nice, isn't it? So one thing I haven't yet discussed is why we split the arguments of ZipWiz into two parameter lists. By the way, the proper name for this technique is called currying. So you might remember from the lecture Generic Functions Part 1, where we saw that currying helps with type inference. So let's have a look at the concrete examples here. So let's take ZipWiz and create a new version that doesn't use currying. So we'll put all the arguments into one parameter group, and let's call it ZipWiz uncurried. Now we are going to delegate the implementation to ZipWiz because we just want to test type inference. And let's try to call ZipWiz uncurried for this expression. So we'll say ZipWiz uncurried, and we put them in the same parentheses. Does it compile? Let's try it out. Yes, it does. So actually, it doesn't matter for this particular example because the combine function we use, product.apply, doesn't need type inference. As we can see, it's a function from string to double and returns a product, so there are no type variables here. However, if we try to zip two pair of double, like product of prices and product of prices, and we use the list apply method as a combine function. So if we try to combine this expression, what will we get? We get a compile time error that says missing parameter type for the expanded function. And we see here that the first argument of this combine function was inferred to double. This is because product prices is we know the type, it's a pair of double, but we were not able to use the type of this one because, as we saw in the lecture, type inference is done one set of parameter group at a time. So we cannot use information from this argument to infer the type of the update function. But if we do use the normal zipWith method, so if we do use currying, now this method compiles perfectly well, as we can see. So currying is not mandatory. We could do without it, but as we can see, it's a good practice to work around any kind of type inference limitation like this one. Cool, so we are done with the first exercise. I think it was a good warm-up to get familiar with type parameters and how they work with type inference. So I suggest we take a short break now, and I will see you soon for the next exercise.